Leutheusser. We're happy to have Sam Leutheusser from the Institute for Advanced Study tell us about emergent local physics in quantum gravity.
Thanks. Thanks for the introduction. Yeah, thanks very much for the invitation to come speak here. So today, I'll be talking about the idea of emergent local physics in quantum gravity. And I should say a lot of this is work with Hong Liu at MIT. Okay, so generally, I think it's fair to say that we do not fully understand a non-perturbative description of quantum gravity. What are the constituents? What are those quantum mechanical degrees of freedom that make up that? Oh, good. Yeah. What are the degrees of freedom that make up those fundamental constituents? What are their dynamics? So we don't fully understand that. But if we think about, okay, what does it mean? What does it mean to have a theory, a quantum mechanical theory that describes gravity? Then it's sort of widely believed. Oh yeah, good. So what does it mean to have a quantum mechanical theory that describes gravity? Well, we would like, in some limits of that theory, when we can define a theory that maybe has some parameters. It's a quantum mechanical system characterized by various parameters, and when we take certain limits of that system, it should describe the things that we see in the real world. Like it should be able to describe gravitational phenomena. And in particular, one of those aspects of when we think about how do we describe gravity, well, we describe gravity by the curvature of space-time. And so even though we imagine that there's some fundamental theory that's just a quantum mechanical theory of some potentially completely abstract degrees of freedom, somehow coming out of that theory should emerge concepts such as space-time, causal structure, the various things that we use when we describe gravity, when we describe classical gravity in particular. So in particular, the picture of this idea. Now it's stopped. Good. The picture of this idea is that we might have some abstract degrees of freedom. I mean, here I just drew them as spins. They're described by some quantum state. That's what I mean by having quantum mechanical theory. I have a Hilbert space. I have some states, and I'm able to describe the dynamics the dynamics of that theory in terms of some dynamics in that Hilbert space. And somehow out of this picture, which is just the quantum mechanics of some abstract degrees of freedom, there has to emerge something that looks like a manifold, and a manifold that can be curved and maybe obeys Einstein's equation or some other higher derivative gravity theory in an appropriate limit. Okay, so this is the general idea, and there are various ideas, particularly from string theory, where we believe that those concepts should be coming out of this sort of picture. So today we're going to ask the question, how does this happen? Good. So in particular, we're going to talk about a very controlled setting in which this happens. So in the previous slide, in general, we believe that this is the case. There's some quantum mechanical degrees of freedom, and somehow they're describing gravity. There's a very controlled setting in which we can ask these questions, which is that of the ADS-CFT correspondence, which I'll just quickly review for people who don't think about it all the time. Roughly, the idea is that there's some quantum gravity theory in d+1 dimensions. So here you can picture that as this green disk here, and those blue squiggles are just schematics of there's some propagating quantum gravity degrees of freedom. And in this particular picture, you might imagine that's like type 2b string theory. And then on the boundary, which is would be this black circle here, there's a conformal field theory. And what the ADS-CFT correspondence says is that quantum gravity theory is mathematically equivalent to the conformal field theory, which is just a particular type of quantum field theory with some extra symmetries. Okay, great. So this correspondence has been around for 30 years now, and so why is it still worth studying? What are the interesting questions we can ask? Well, one reason it's interesting is it's a concrete realization of this idea of the holographic principle, which is the idea that gravitational systems, it looks like we have a larger number of degrees of freedom than we really need to actually encode the physics. So here, it looks like we need a full d+1 dimensions, degrees of freedom, and secretly that's all encoded in a d-dimensional theory. And the other reason this is a fruitful place to study is because it allows us to treat gravity as emergent from a particular quantum mechanical system. So, in general, and people are actively working on this, trying to understand what is that quantum mechanical system outside of these ADS spacetimes. And so here we're in this very concrete setting where we know what the quantum mechanical system is. And in principle, it's just a regular quantum mechanical system. It's a CFT, it's just a particular type of quantum mechanical system without any gravity that in principle we know how to describe completely. Okay, but then you might worry, well, okay, our universe doesn't really look like ADS at large scales. And so an important question to answer in the context of this is about the emergence of physics in local subregions. And so in particular, here what I've drawn is some finite causal diamond that's just, somewhere within an ADS space-time. And in principle, there's no fundamental difference between semi-classical physics in that diamond versus if it's in ADS or if it's in a space-time with other asymptotics, any other value of the cosmological constant. So what we can hope is that if we can understand how does the local physics in a region like this emerge from ADS CFT, where we have very concrete theories that we're writing down on the boundary, how can we use the lessons that we learned from that? And maybe if we can understand local physics, we can extend those lessons to other asymptotics, and in particular, maybe asymptotics that look like our universe with a positive cosmological constant.
Sorry, what do you mean by no fundamental difference? The causal structure is completely different.
So the asymptotics.
The causal structure of lambda versus positive versus negative is completely different, right? So what do you mean by?
Sorry, the asymptotics of the region, like this. In principle, if I make this region smaller than the ADS scale, in principle, there's nothing I can measure within that region that really knows that I'm an ADS.
So,
yeah.
So locally.
Yeah, locally. Yeah. It's important here that here I need to be talking about local subregions that don't get anywhere near the boundary. Otherwise, I know that I'm an ADS. Yeah. Good. Okay. Great. Okay. So what's the highest level story of the ADS CFT correspondence? Well, I told you it's a duality between some gravity theory in the bulk and a conformal field theory, just some quantum mechanical system on the boundary. And so at the highest level, what this could mean is that we have, so I want my gravity theory to be a quantum gravity theory. So it's described by some states in some Hilbert space. So it means that there should be some one-to-one correspondence between states of that quantum gravity theory and states in the conformal field theory on this side. So one of the simplest examples, which we'll come back to many, many times in this talk, was proposed by Malvicena in 2001, which is that if I now take two copies of the conformal field theory, a left and a right copy, and I can tangle it in some particular entangled state called the thermofield double, then that should be dual to a quantum gravity state that describes the physics in this eternal ADS black hole geometry. And so for those who are not super familiar with Penrose diagrams and don't think about it all the time, here this is just sort of a compact way of drawing an ADS black hole. And in particular, it's a black hole. It has the singularity here in red, and then there's an asymptotic boundary. That's the really special to ADS thing, is that we have this time-like boundary out here. Okay, but what I want to emphasize is that if you look at these two pictures, in a sense, they look nothing alike. There's way more going on in this left picture than is going on in the right picture. In the right picture, I have two copies of some CFT. I don't have any sort of there's no sort of connection between them. They're just in some entangled state. And yet in this left picture, I have all of these phenomena whose description is not at all obvious from the CFT perspective. There's sort of well-known techniques that sort of tell me, okay, if I can maybe describe the physics in this right region in terms of the right CFT, physics in this left region in terms of the left CFT. But what about all those other features of the diagram? There's horizons. How do I describe those from the perspective of the conformal field theory? I'd say from this picture, it's not at all obvious how to do that. There's interior regions. How do I describe physics in those interior regions? And in particular, what we might want to imagine, especially because we believe that we are observers who are living in a universe where there is a quantum theory of gravity. There really is dynamical gravity. How do we describe the experience of an observer who's falling inside that black hole from the perspective of the CFT? Okay, so there's a lot of, so there's lots of things to learn about the emergence of this space-time from the conformal field theory perspective. And so what I want to emphasize is that that picture that I just drew for you was that was a classical Penrose diagram. It's just, it's a solution of Einstein's equation with negative cosmological constant. That's what it is. And so that is, we believe, should be the correct description in a semi-classical limit of the gravity theory. In a limit where we can just describe it as being on some fixed space-time. And by the usual dictionary between the gravity theory and the conformal field theory, this corresponds to a conformal field theory with a huge infinite number of local degrees of freedom. So throughout the talk, I'll use this parameter n. N is just schematically the number of local degrees of freedom that I have in my boundary field theory. So, I'll just use it schematically, but if I had, n equals 4, with gauge group SUN, it would really be n squared, but I'm just going to schematically write it as n. Okay. And so in this limit is when a classical geometry emerges. That's when that picture on the left, we believe is a good description of the quantum gravity theory. And so that means that we need to understand something like an n to infinity CFT, or at least perturbation theory in 1 over n around that CFT. And all those questions that I was asking were questions about the emergence of the bulk spacetime. And in particular, we want to understand, where does the causal structure come from? How do I have a non-trivial causal structure between the left and right CFTs in that picture? How do I describe that from the CFT language? How do I describe just general spacetime subregions, like this diamond that I drew in the center of ADS? I'd like to understand how do we describe the physics in those regions from the CFT? And in particular, also how can we describe the notions of infalling time? How do we use the conformal field theory to construct operators that are dual to evolutions of observers falling into the black hole in the geometry? So these are the kind of questions we're going to be interested in today. I'll talk mostly about the first two, but if you have questions about infalling times, let me know after. Okay, so I've said it many times, but just to emphasize, the main thing we're going to be interested in today is how does the bulk spacetime emerge from the CFT? And then, in particular, how does that radial direction come out of it? How do I get things like connections between asymptotic theories? Good. But I want to make this question a little more precise, which is I want to ask, what is the mathematical structure that is responsible for the emergence of these bulk geometric objects? So I want to understand, there's all these geometric features on the bulk picture that appear in the semi-classical limit. How do those features come out of the mathematical structure of the CFT? And so the slogan for right now is that bulk spacetime is a geometrization of what are called emergent type 3-1 algebras in the boundary. So at this moment, I haven't really said what most of those words mean. And so hopefully by the end of the talk, we'll make sense of this statement. But what I want to, but basically, in a nutshell, what I want to say is we're going to find that when we take seriously the perturbation theory around the 1 over n perturbation theory of the boundary theory, we're going to find that there's a dramatic changes in the algebraic structure of that boundary theory. How do algebras relate to each other? And it's going to look very strange. From the perspective of quantum field theory, it looks like a very strange quantum field theory. It doesn't obey lots of the nice properties that we like. But if we can find a nice mapping between those algebras that we have on the boundary and these dual algebras of operators in bulk perturbation theory and effective field theory, then all of the weird properties of these emergent algebras get translated into very nice geometric properties of the bulk. And so in a sense, the bulk gives a beautiful geometric description of all these weird algebras that we find on the boundary. And in particular, notions such as subregions and causal structure are going to be related to the properties of these emergent type 3 algebras. Okay, so are there any questions at this point? That's just sort of the motivation.
I do have one. I know what the type 3 algebra is, but what do you mean by immersion? In the sense that it will be some scale at which you will see these features to appear that will resemble from the point of view going close to the horizon, something like that. Will be some notion of getting close to the horizon or something like that? Or?
So here what I mean is emergence in the large n limit.
So that's not right. Okay.
Yeah. So yeah, it's emergence in the large n limit, and one of the things that we'll actually argue is that it's actually necessary that this type of structure emerges in the large n limit, because otherwise we would not be able to describe the causal structure that we're supposed to be able to.
So the
describe.
question is, you will be able to see if you want to describe the existence of the horizon, or you will also be able to say something about where it's located, some.
So we'll be able to see the existence of the horizon. And then if you grant me HKLL reconstruction, a particular reconstruction procedure in the exterior of the black hole, then we can actually tell you where the horizon is with these infolding operators. Yeah. Okay, great. Okay, so as a quick outline for the talk, first, in case everybody's not familiar with it, I'll go over the idea of algebraic descriptions of quantum systems. Then I'll talk about large n limits and what's called the Gelfand-Neymark-Siegel or GNS Hilbert space. Then I'll talk about these fancy type 3-1 algebras. It's not too important what the type 3-1 means. I'll try to give some intuition for what that means. And then I want to talk about some applications, the relation to causal structure. What is this actual map that takes us between boundary algebras and bulk subregions that geometrizes these features? And then hopefully I'll have time to talk about a nice application, which is related to the performance of what are called asymptotic quantum tasks. Okay, great. So I'm going to say the word algebra a bunch in this talk, and I apologize for that. And hopefully it doesn't start sounding weird or anything. But why am I interested in algebras? So one reason, I'm going to give you 3 reasons why I think they're interesting: a conceptual, a technical, and a pragmatic reason. So conceptually, they're very nice. They're operational in the sense of, okay, well, what is an algebra? An algebra is just the collection of all possible observables that can be measured, in the lab or by a particular potentially restricted, observer who's probing some system, who's performing some experiments. Okay, they're very idealized versions of that, but in principle, that's what they are. They're flexible, and they're flexible because they allow us to describe situations in which maybe we can't give a Hilbert space description. So even when we don't have a preferred Hilbert space existing, so for example, in time-dependent spacetimes, famously, it's hard to decide which Hilbert space representation should I be working in. I can still give a unified description in terms of algebras. And also, even when I start talking about subregions in a relativistic quantum field theory, I have to start talking about algebras. I can't be talking about local Hilbert spaces. So let's come to that point a bit. And this is related to what type 3-1 really means. So imagine that I'm in a quantum mechanical system and with a finite number of degrees of freedom. Okay, in that case, usually the way that we describe this physics is we say there's a region we can observe, that's some subset of the degrees of freedom, and we put those degrees of freedom, we describe the state there by some Hilbert space. So here is this HO, the observable Hilbert space. But then, we know that maybe we're not describing everything, so there's some environment Hilbert space, and then there's some collection of degrees of freedom that we call the environment that we don't know how to describe. We're not able to measure. Okay, so in quantum mechanics, the total Hilbert space of the system is just the tensor product Hilbert space. And the local operator algebra, the algebras that I can perform, in the lab on these subset of degrees of freedom, we take just to be the algebra of all bounded operators on the Hilbert space. So I'll use this curly B a couple times. That just means all of the bounded operators on that particular Hilbert space. Okay, and good. And so if I have a global state psi in the Hilbert space, so this is sort of the global description. How do I describe the local physics, the actual degrees of freedom that I can see? The local state is, as is well known, is described by a density matrix. I form this operator, and I take the partial trace where I get rid of the degrees of freedom that I can't observe. If that state is entangled, though, then we know that there's actually not a definite state on in this Hilbert space HO. This density matrix will not be rank 1; it will be higher rank, and the interpretation of that is that I'm sort of in some mixture of states. I'm not in some definite state on that Hilbert space. This can be quantified here in this nice case of pure states using the von Neumann entropy, which is just some functional of this density matrix. If this von Neumann entropy is positive, then in this case, the state is entangled and I don't have a definite state on my Hilbert space. Okay, so that's the very familiar story in quantum mechanics. But what about in relativistic quantum field theory? So here what I've drawn is a Rindler decomposition of Minkowski space. Here there's a t = 0 slice. Well, you might say, okay, I just formulate the theory on that t equals 0 slice. Let me write down some degrees of freedom on that Hilbert space, and then chop it in half and say that I have access to the left degrees of freedom, but not the right degrees of freedom. This looks a lot like what we were just talking about. So naively, what we would say is there's a Hilbert space for left degrees of freedom and a Hilbert space for right degrees of freedom. But in fact, this is inconsistent with relativity. This has actually been known since the days of Fermi, and was very sharply was sort of sharply stated in this paper of Hagerfeld in '94. So it's been known for a while that this tensor product factorization is inconsistent with relativity. And related to this is, a well-known fact that the von Neumann entropy diverges. If I try to compute the von Neumann entropy of this left these left degrees of freedom in some sort of regularization scheme, as I remove the regulator, that von Neumann entropy always diverges. And this is a reflection of the fact that all finite energy states are infinitely entangled between the left and the right degrees of freedom. But what I want to emphasize, and especially about this flexibility of algebras, is that even though these Hilbert spaces don't exist, the algebra of operations are still well defined. So the algebras are flexible in the sense that they let us use the exact same language to describe finite dimensional quantum mechanics, as well as this relativistic quantum field theory, which of course has an infinite number of degrees of freedom. Okay. And another reason why algebras are useful is that they allow us to generalize ideas from quantum information theory, which has been very, very useful in the context of ADS-CFT in recent years, to relativistic and thermodynamic systems, systems that really have an infinite number of degrees of freedom. So let me just say a few words about that. Good. So even though we were able to describe these local systems in the two cases by algebras, there is a fundamental difference between those algebras. So we had local operator algebras, both in finite dimensional quantum mechanics and in relativistic quantum field theory, but those algebras are of a fundamentally different nature. And this is neatly summarized by a classification of von Neumann algebras due to Murray and von Neumann, where in the quantum mechanics case, the local algebra is what's called a type 1 von Neumann algebra. It's equivalent to the algebra of all bounded operators on some Hilbert space. Whereas in relativistic quantum field theory, there are these much more exotic objects called type 3-1 algebras. And I won't go into the mathematical details of what that means, but related to the discussion on the previous slides, essentially these are algebras for which we can't define some finite, well-defined notion of entanglement entropy, and in fact we actually can't even define a notion of a localized state. So we lose a lot of the structure of quantum mechanics. Good. For interest of us, one way to say it is that this was a case in which a pure local state existed. That's just saying that there's a local Hilbert space. Whereas here, there's no such thing as a pure local state. There's no pure states on the localized system. Good. So what these type 3 algebras are doing is they're encoding the idea that not all information is accessible. And this is a great thing because that's what we think when we talk about subregions. If I'm talking about a subregion, it means that I don't have access to all of the information that's in principle accessible in the system. Good. And then what I want to emphasize in the quantum information theory perspective is that, okay, we unfortunately, we've lost all this nice structure in finite dimensional quantum mechanics that we usually use to describe quantum information theory. But it turns out that there's been lots of work, in particular this work of Tomita and Takasaki, that allows for lots of finite dimensional quantum information theories to be generalized to the infinite dimensional setting. And usually that involves something called this modular operator, which you can think of as the product of the left reduced density matrix times the inverse of the right reduced density matrix. And so this is an operator that actually generalizes well to the continuum. You can think about that as, well, row left has a bunch of eigenvalues going to 0 in the continuum limit, but row right has a bunch going to infinity, and so this operator actually survives. Okay. And the pragmatic reason why algebras are useful, so this is, this was to emphasize that the algebras are useful for describing these local systems, even with an infinite
You
number
have
of
to see
reasons.
how to define rho L, no? Because now you don't have the trace of a semi.
Oh, yes, good, yeah. So this is a schematic notation, yes, yeah, so we can't even define row left or row right. But we can think about this operator delta as some sort of continuum limit of those operators that I could hopefully define in a regulated theory. Yeah. Good. Yeah,
So is it obvious that I can't, like, so the label that you just gave for the RQFTs is that there are no like simple pure local states.
mhm.
But is it obvious that, I don't know, I'm thinking, if you think of the Fox-based construction of a quantum field theory,
Yeah.
you see like the one particle system is like the one particle sector of this is like isomorphic to just the quantum mechanical system. So is there a reason why I can't just take a particularly simple quantum field theory state, trace that out, and get something on the left factor or the right factor that is like a nice pure simple state?
So good. Let me say, so that the important thing here is that we're talking about subregions.
Right.
So even like, if I do a Fox-based construction on a complete Cauchy surface of my manifold,
Sure.
then that algebra actually will have pure local states for the complete thing. What happens is when I try to go to subregions is when I lose that ability.
But you can go to subregions if you just have a quantum mechanical Hilbert space.
Yes, if I have a quantum mechanical Hilbert space with a finite number of degrees of freedom, then I can.
Right.
Yeah. Like literal degrees of freedom, right? So
Yeah.
like quantum field theory is like, I have an infinite number of degrees of freedom, right? So, yeah.
So yes, this RQFT would be a relativistic quantum field theory and local operators in a subregion. And for the algebra of local operators in a subregion, well, this algebra is a type 3, or type 3 one. So yeah, if you have to take a subregion, a proper subregion of your space, right? So you can think of quantizing a free field on a circle, right?
Yeah.
Okay, that definitely there is a equal space. The algebra of local operators there will be type 1, but then if you take half the circle,
If you try and
local
vertically
operators
trace
on the
Yeah.
half circle will be type 3 algebra.
But this is a statement about the algebra. This isn't a statement about like any one particular state.
Sorry, yeah, no, this is a statement about the algebra.
Okay.
Yeah,
I think that was my.
Yeah. And what the algebras do is they encode the fact that in the Hilbert space, in the global Hilbert space, every single state is in a heuristic sense infinitely entangled between any subregion and its complement.
Okay.
Yeah. Of course, okay, yeah. In the continuum limit, because we don't have a tensor product factorization, we can't actually define entanglement, but with a regulator, we can see that the entanglement entropy diverges. Yeah.
These algebras are bad, but they're not terribly bad because all the ones that we encounter in physics are called hyperfinite.
Yeah.
So they can be obtained with a limit that on the countables, right? That are countable.
Yeah.
And
So
then you send them to infinity.
yeah. There's very nice, there are very nice sort of like really concrete and computable constructions of these kind of algebras. So even though they look kind of exotic, but
I guess like probably the most lowbrow construction you could take is take like a free relativistic QFT at the Fox space and truncate it at the end particle sector, and then take n to infinity, and this will give you like.
No, you don't want to
Some
do that
parameters.
because
You need a local algebra.
it's not local. The
The
equation
key
like-
property of these things that also extends to other algebras that are type 1, type 2, etc., is that there is a cyclic separating vector, right? That's really what tells you that many of the properties that you use in a Fox space construction don't hold, because for the Fox space and Fox space construction, clearly there is no such thing as a cyclic separating vector.
Yeah. Intuitively, what's the conflict between relativity and factorization? Is it that you have to choose a particular regular?
Locality, it's called locality.
Locality, but the point.
Yeah, it's locality. So if you take an atom that goes brrr,
yeah.
and then you look at another atom in the ground state, right? If there was
This is-
factorization, this atom will never be excited. But we know that it's excited. How do you describe that? Because you cannot factorize the Hilbert space.
Yeah. So this Fermi 2-atom experiment, where you can see that even if you have that excitation, basically because I have Hamiltonian evolution and the Hamiltonian is bounded below, you can show that there's basically a function that admits an analytic continuation in the upper half plane. and if I had that positivity property, then that function cannot vanish on a, which would be the commutator sort of between operators on this space-like atom from this atom, that function can't vanish on an open interval, because by Cauchy's theorem, it would have been 0. So, yeah, so that's sort of the mathematical reason, but yeah, it's basically if I want to have like a finite propagation speed at the speed of light, then I need these algebras to describe that situation. Yeah. Okay, good. And so the final reason that I want to give is pragmatic, which is just that, you know, these algebraic techniques have been useful in recent years. They've been useful in sort of proofs of the Bekenstein bound and the QNEC, and for arguments for the C theorem. But the useful thing I want to talk about today is they've provided some new insights into quantum gravity. Okay, so let's come back to the large N limit. And so we want to be talking about conformal field theories, where we're taking the number of local degrees of freedom to be very, very large. So, you know, consider some conformal field theory with n by n matrix degrees of freedom. So you might think of this theory, you know, with your matrix operators. At a finite value of n, there's a well-defined Hilbert space. And actually, the full algebra of operators, so everywhere on the space-time, on the entire manifold, they generate what's called a type 1 von Neumann algebra. So just, you know, it's the bounded operators on the whole Hilbert space of that particular CFT.
But in a subregion, the theory, you have a type 3.
Yes, in a subregion of the theory, you have a type 3 already in this case, because it's a relativistic theory. Yeah. Now, if we want to take the large N limit, we have to do that carefully. And so the way that we take the large N limit is we imagine that, you know, we have this sequence of CFTs, which is indexed by this parameter n. We choose a sequence of states, so we choose one state in each of those CFTs for different values of n, and we define the large N limit by keeping only the operators whose correlation functions, so we study the sequence of correlation functions of operators in those states, have a well-defined large N limit. And importantly, what happens is that not all operators are going to survive that limit. Some of them are going to have infinite correlation functions, and they're going to drop out of the formal description of the large N limit of that theory. And because those operators drop out of the theory, there are dramatic changes to the structure of the operator algebras that are defined in the large N limit. Okay, so that's the procedure. And how do we get a Hilbert space to describe the large N limit?
So in this algebra, in this construction, you take a set of states, psi n.
Yeah.
Then you compute the correlators on that state.
Yes.
And you keep only the operators that have finite correlators on that state.
Yes. Yeah.
That probably defines an algebra A0, and then you complete it in the weak or strong node.
Yeah. So good. So that algebra that we define in that way, it's, you know, it's basically an algebra defined by correlation functions. It's actually not a von Neumann algebra. It's not been completed yet, and so we complete it using the GNS construction. So these operators that survive the large N limit, they form some state-dependent algebra. So there's an algebra that's basically defined by the limits of those correlation functions. And so in that sense, it's a state-dependent algebra. Oh, wrong way. And this large N limit of the states defines some new states on that algebra. Formally, this is an algebraic state. It's not necessarily a state vector like I've drawn it. And the set of states, so if I think about acting this algebra on the states, okay, then I get some new set of states. I have, you know, I take states and I act a bunch of operators on them, I get a set of states. And what's crucial is that Gelfand, Neymark, and Siegel showed that that set of states can be closed into a Hilbert space, a genuine Hilbert space. Okay.
So that depends on the state being cyclic or
so it can be done in either case. If I want to get a faithful representation of this algebra, then I need a separating state. Yeah, but it can be done in any case. I just might have this Gelfand ideal that I have to quotient by if I don't have a separating state. Yeah, but basically by construction, I'll always get a cyclic state out of this. Good. So what is this GNS Hilbert space? Well, in this setting, it's basically the Hilbert space that captures the small excitations around this sort of limiting state sub. Okay. And then, what we have is that, okay, now we want to close it into a von Neumann algebra. So we denote the closure of this when we close it on this particular Hilbert space in the weak star topology. And that gives us a von Neumann algebra m sub psi. Okay, so now it's one of these algebras that we were talking about before.
Which is also unique regardless the cyclicity of the state.
Oh, sorry,
The extension.
this extension. Yes, yeah. So yes, in this case, I think it will be. Oh, yeah. Okay, it's unique.
In the cyclic case, I think it's unique the extension, right? For you make
So here, good. Sorry. So here I always get a cyclic vector because in the GNS construction, basically, I basically define it so that I do get a cyclic vector. I say it's the closure of this set of states. So I'm dense in that set already. Yeah.
Wait, I'm sorry, we said cyclic vector a few times. What is it? What is
Oh,
cyclic
good.
Vector?
Yeah, cyclic.
That's not an aside.
Yeah, sorry.
That's
Yeah,
not
sorry.
what-
Yeah, that's some jargon. It basically it's so a cyclic vector is some state. For example, like the Minkowski vacuum is a cyclic vector for Rindler algebras. It's a vector such that if so it's defined with respect to a vector in an algebra. So if I have some algebra here M and some vector omega and some Hilbert space H, a cyclic vector means that M acting on omega is dense in H. Yeah. So yeah, it just means that if I close this in the inner product of H, I get all the states. Yeah, I don't miss anything by taking this vector and acting with the algebra. Good. Okay, so this is the story on the boundary. So what's the story in the bulk? Well, the story in the bulk is very simple.
And sorry, do you get a factor?
So in the situation I'm going to talk about, which is leading order in the large n limit, you do get a factor. Yeah. Good. Yeah, if you have non-trivial charges turned on, then you might not get one. Yeah. Good. Okay. Good. So what's the description of the bulk Hilbert space? In perturbation theory around this small G Newton limit, we believe that the quantum gravity state, whatever it may be, we can't give an explicit description of it in some non-perturbative formulation of quantum gravity, but we believe that the physics about such a state can be described by a classical solution of some classical gravity theory. Okay, so I'll denote that by chi psi. And then we can take that solution and quantize perturbative bulk fields around it. So, there will be, in this limit, there'll be small excitations around the quantum gravity state. And we believe that those are described by some effective field theory, where we have these perturbative bulk fields around that background solution. And the operators that we construct out of the perturbative bulk field operators, they form an algebra, which is this algebra m tilde of psi. Good.
Which operators are we including here?
So-
Now the notion of local is less clear because
Yeah.
which operators are the ones that
So
can I
like,
exponentiate them? What can I do with them?
which operators are included here?
Yeah, because
I guess they're the operators that are defined in the effective field theory around.
but like already in local algebra, we normally don't talk, for example, about defects, which are local integrals, so operators. So there is some restrictions which are implicit.
Defects are included
Defects are included
Yeah.
as operators.
if they're in the same region.
Okay, so you're saying
Yeah.
even exponentiating these.
Yeah. They're included because basically, because we will take this closure. So we're allowed to exponentiate operators because we've closed the algebra.
So how does this mirroring work in that case? Not much of a device. Because normally I thought you take a local operator and you smear it, and that's what gives you all the defined operators for potential smearings. So you don't have to worry about that when it depends on a contour or something.
If they are found, then we better be smeared.
Yeah. So really, right. Like it should be operators that are like e to the I integral f(x). Yeah.
Something like this.
Yeah.
It's not exactly.
Not exactly, but when you take the completion.
Yeah. Okay,
Yeah.
okay, fine, thanks.
Yeah. So like these are the elements of the algebra like that.
Okay.
Yeah. And
So again, you started with one vector, then with a set of operators, then you multiply them and you form an algebra. But then this algebra is not from Neumann because you have to enlarge it and close it in the operator norm, in the weak or strong operator norm, until it's a von Neumann algebra is also this, equal to the closure of the closure. to the commutant
Yeah.
of the commutant. So commutant, you take double commutant, you get Partiandro. So you have to first start with the states and then enlarge.
Yeah, there's a lot of steps to go from the fields to these algebras of bounded operators. Yeah. Good. Okay, so then what's the statement of semi-classical ADS CFT duality? Okay, so at a finite value of n, the statement was this equivalence between Hilbert spaces, that there's some quantum gravity theory in the bulk described by some Hilbert space, and that should be equivalent to the CFT Hilbert space. But what I emphasized a couple times is we don't know some independent definition of that Hilbert space at the time, right now. But what we do know is that in the large n limit, we can phrase this equivalence. So we're zooming in basically on some subsector of these states, and we can phrase the equivalence as equivalence between this GNS Hilbert space of these operators that survive the large n limit, and the perturbative bulk field operators. Okay, and in algebraic language, that means that the operator algebras acting on these Hilbert spaces are equivalent. Okay. So one thing I just want to say that I think is sort of a nice story in this picture is the idea that I emphasize that when we define this algebra, we have to take the large n limit in some way, and we have to be a bit careful defining the sequence of states. And that leads to an interesting phenomenon, which is the idea of the fragmentation of the CFT Hilbert space. So at a finite value of n, if I have any states psi and psi prime in the Hilbert space of the CFT, of course I can find some operator in the CFT that takes me from the state from the state psi to the state psi prime. So schematically, we have this picture here. So even if we believe that there's some state that has different semi-classical physics from a different state, at a finite value of n, all of the states are connected through operators in the algebra. But when we take the n to infinity limit, if these states correspond to different semi-classical geometries, the operators that connect those states drop out of the theory. And so in particular, we go from that picture to this picture, where now we have disjoint Hilbert spaces that describe the semi-classical physics, around different states. So this Hilbert space fragments into these disjoint sectors, and so that's why the state dependence in defining these algebras was important. Okay, so this has been sort of very abstract and general. I've just said, oh, there's some sequence of states psi. So let's come back to our favorite example, which is the thermal field double. So for those of us who are not familiar, the thermal field double is just this nice state here. It's some particular entangled state between two copies of a conformal field theory, where I just am, I weight all the terms in the sum by this sort of Boltzmann factor. Okay. Good. So what happens with this state is this is a situation in which I have two copies of the theory. So in particular, I'm going to have two copies of the algebras that survive the large n limit, a left copy and a right copy. And depending on the temperature, so remember, this is a different sequence of states depending on the temperature. Sorry, if we go back, back to this slide. This is so really this is a family of states parameterized by beta. So if I choose different values of beta, then I actually end up getting different results for the emergent large n algebras. So in particular, if I'm below what's called the Hawking-Page temperature, then the algebras that I get acting on this GNS Hilbert space are those type 1 von Neumann algebras, like the finite dimensional von Neumann algebras, although they are actually still infinite dimensional. But I get these type 1 algebras, and the bulk dual of that picture is the physics that I'm describing is the physics in the dominant saddle in that case is thermal ADS. And so I'm really describing two independent copies of ADS whose small excitations are in some entangled state between each other.
Can you give us an idea of how you prove this?
Oh, of how to prove this? So this basically it's more of like a self-consistency check in the sense that you look at the properties of the thermal correlation functions of single trace operators. And basically what you find is, so yeah, good. So these algebras are all defined by correlation functions. And if you look at the properties of those correlation functions as functions of time between the single trace operators, basically what you find is that there's a discrete spectrum of frequencies when you Fourier transform the thermal 2-point function. And then also because you have large N factorization, those operators, their commutators are just complex numbers because I have large N factorization. And so this just describes sort of like a generalized algebra of canonical commutation relations. And then those have all been classified into whether they produce type 1, type 3 algebras. And so in particular, what happens is that because the Fourier transform of the 2-point function has a discrete spectrum in this case, and the algebra that I get in the large N limit because of large N factorization is a canonical commutation relation algebra. It turns out that that was proven either by Iraqi that's type 1. Whereas in the case where I get a continuous spectrum for the Fourier transform of the thermal 2-point function, then it's proven that gives me a type 3 algebra. Yeah. And so yeah, good. And so that's the next.
What is, I'm sorry, what is HP?
Oh, sorry. Yeah, this is the Hawking page temperature.
But suppose you put the CFT in the boundary, so the boundary of ADS is locally ADS, but it's actually a flat space, right? You don't put it,
Oh, sorry. They
I mean, just locally asymptotic ADS space requires to have a base manifold that is curved in order to have a phase Hawking page transition. Right?
Oh, sorry. Yeah. So sorry. Here my boundary my boundary manifold is always a circle. Sorry, the spatial manifold of the boundary, or a sphere.
A sphere.
Yeah, sphere. Yeah. So this right. So this happens at 0 temperature in the flat limit. Yeah.
So you don't have this separation.
I mean, you don't have this. I guess THP goes to 0. So either you get the vacuum.
So it only works when you have your CFT defined on a S2.
Yeah. Here you need a sphere so that you have a scale for the Hawking page transition. Yeah. Good. Good. And so above the Hawking page transition, the algebra that we get is one of these type 3-1 algebras. And so yeah, you can see that from the spectrum of the 2-point function.
And this one instead of lambda comes from.
Good. So yeah, so the one okay. We know that it's this type 3-1 because we can construct these half-sided modular inclusions. And it was proven by Borchers that you can only have those in type 3-1 algebras. So I don't know if I have a good intuitive explanation of that. But basically, I mean, yeah, the bulk picture is maybe the most intuitive explanation of that. Because we know that this algebra is dual to this subregion in a local bulk effective field theory. And so their general arguments of Fried and Hagen apply, and you can say it's a type 3-1 algebra. Yeah. Okay, great. So good, yeah. So I just sort of hinted at this a bit. So one way that we know that this is a type 3-1 algebra is we can construct something called a half-sided modular inclusion, and you can use that algebraic structure to define what are sort of infalling time operators in the bulk. So you can go to the boundary theory, see that you have this algebraic structure. It's a structure of a structure within the modular theory of the boundary, and using that structure, you can define these infalling times. And so I won't go through all the details of that, but let me say that just basically because these algebras were type 3, we were able to define this one parameter family of unitary operators with a positive generator that implements infalling time. So these are operators defined in the boundary theory, but if you evolve an operator, so this is an operator somewhere in the bulk, but we map it to the boundary using HKLL reconstruction, a standard reconstruction procedure. And what we can show is that this operator U of S has the property that it evolves this right operator to an operator that goes into the interior. And in particular, this operator this evolution by U of S respects the causal structure. So not only, if I fix some left operator on the left side of the black hole, not only do I need to evolve by enough amount to get across the horizon, but I actually have to evolve all the way until I cross the forward light cone of that operator. So these boundary operators actually encode the bulk causal structure, and the construction of them required the emergence of this type 3-1 algebra. Okay. So now let me talk more generally about the idea of subregion subalgebra duality. So far what we've discussed is the bulk duals to the large n limit of the full boundary algebra. So we've always been taking, all of the operators on the, everywhere in the spatial manifold, and then talking about the large n limit of that algebra. Now, what happens if I start talking about large n limits of subalgebras? So, of course, the boundary theory is itself a local theory. It has subalgebras of operators associated to local subregions. So what happens when we take the large n limits of those? So let me just first say that, the idea of semi-classical ADS-CFT and the identification of global algebras implies that the subalgebras must also have some identification between them. But in the semi-classical limit, the bulk theory is that of quantum fields on a fixed spacetime background. This is just some effective field theory. And that has a very particular structure. In particular, it's a local theory. So to any bulk subregion, I have associated subalgebras, and those subalgebras obey various relations that are constrained by causality and the equation of motion of the bulk theory. Right? So in the bulk theory, I have these operators O of X. I can restrict my spurion functions to certain regions and construct these kind of things. So I can construct subalgebras. I can construct subalgebras that are associated to local subregions in the bulk. And they have these special properties. In particular, in the bulk, this is a regular quantum field theory with an equation of motion. So all of the operators can be defined in the neighborhood of a single Cauchy slice. And the Cauchy slice can be decomposed into subregions like these red and blue regions here. And after we do that, we actually get from these general arguments that there's a type 3-1 algebra associated to each subregion in that case. Okay, so how is it possible that the boundary theory is going to be able to reproduce this structure? Well, then we need to look more carefully at the algebraic structure of the large n limit. So what I already emphasized is that the global algebra of all operators on the boundary can undergo all of these sort of dramatic changes in the large n limits. And it turns out that that's also true. It's also true for local algebras, although we don't get something as dramatic as the type of algebra changing, but we get relationships between algebras changing. Okay, so in the large n limit, what happens in the boundary theory? So here what I've drawn is a boundary causal diamond. And usually in a quantum field theory, we have a nice local equation of motion, which we can define on a single time slice. And that allows us to map all of the operators on this red Cauchy slice of the diamond down to this blue Cauchy slice of the diamond. And so it actually shows that those two algebras are equivalent. But in the large n limit, we lose the Heisenberg equation of motion of the boundary theory. And so these algebras do not need to be equivalent, and actually in general, they are not. So another picture is that imagine I draw this sort of intersection of two diamonds here. This is what's a causally incomplete boundary subregion, right? If I look at all the points that are, if I do the causal completion of this, I end up with that bigger diamond. This is a causally incomplete region, but even though it's causally incomplete, because we don't have the equation of motion, it turns out that there's a different non-trivial algebra associated to that region versus the algebra of operators generated in this larger temporally extended region. Okay, so these are the strange properties of the boundary theory that appear in the large n limit.
So in particular, you cannot, the time-like 2 theorem is no longer true in this case?
Good. So in this case, the time-like 2 theorem is true. Good. Yeah. So good. Yeah. Good. Yeah. Okay. So what's true is it's still true. If I have some tube on the boundary like this, then its algebra is still like this, because that good. Yeah. This is still true. But for these sort of stranger subregions, which are not just like tubes, if I take stranger shaped subregions, then the time-like tube theorem actually doesn't guarantee anything. So it actually, it doesn't guarantee anything like this. So right in the usual time-like tube theorem, what it says is that if I can deform, I need to add all of the region, all of the entire region that I get by taking curves that are sort of anchored at the top and bottom of this cube, and deforming them so that they remain always time-like, right? So in this situation, I actually, by the time-like tube theorem, would not get any extra operators in the region. Yeah, good. Okay, great. Okay, so good. So we have lots of new non-trivial algebras appearing in the large n limit, and that's great, because in the bulk, we expect to have type 3.1 subalgebras for any causally complete subregions in the bulk. In the bulk, it's just a regular effective field theory. So the proposal of subregion subalgebra duality is just very simple, that for each causally complete bulk subregion, which I denote by this Gothic B, there's some associated algebra of operators generated by things like this in the effective field theory. And that's dual to an emergent type 3.1 subalgebra in the large N limit of the CFT. And we have way more non-trivial emergent subalgebras in the large N limit, which allows this kind of statement to be true. And let me say this is a sort of a generalization of what's called the usual Ryu-Takenagi prescription to understand which regions are dual to which regions in ADS-CFT. This actually allows us to describe general bulk subregions. Good. So even though I've just said that it's a generalization of Ryu-Takenagi, an important thing is to check that in the cases where Ryu-Takenagi applies, it actually works.
Sorry, but
yes.
I still don't understand what happens in the larger limit. For finite n, the subalgebras in the CFT are type 3 already.
Yes.
So what is the new property?
Oh yeah. So the new property is yeah. So for example, like in that picture I drew, where we had overlapping diamonds like this, let me call sort of this joint region together. Let me call that something like R. And then we have there's a bigger region. Okay, so there's a bigger region. Oh, it's blue. There's the bigger region, which is sort of the causal completion of that. Let me call that R hat. So at finite n, let me denote sort of the finite n algebras like this. We have some Bn of R, and that turns out to be actually equal to Bn of R hat, and these are all type 3.1. But what happens in the infinite n limit is that there's this algebra, which I'll call X, which is basically the large N limit of this, and it turns out that this X of R is actually a genuine subalgebra of X of R. Yeah, and so everything here is type 3.1, but there are some new non-trivial relations, yeah, between them.
And I lose the Hamiltonian just because it grows with n or something like this?
Yeah. So basically, yeah, the Hamiltonian is not one of the operators that survives the large N limit in these cases. Yeah. Good.
But is there still a reasonable way to make sense of time evolution then?
Well,
We don't.
in some cases, yes. So yeah. So sorry, like boundary time evolution.
Yeah, boundary
Yeah.
time evolution. I'd be more worried if you said no about bulk time evolution.
Yeah. Okay. Yeah. So for the boundary time evolution, good. So there you can define. Good. Let me say you can define an operator. Let me call it H infinity. You can define an operator so that the following thing is true. Let me just call it O0. Okay. The adjoint action of that operator on this, you can define an operator such that this is true at n equals infinity. But this operator is not constructed from operators on a single time slice.
Okay.
Yeah. It's and also and then in certain cases, yeah. In certain cases, even that operator is not defined.
Okay.
So like in the vacuum sector, this operator will be defined, but in the thermal sector above the Hawking page transition, even that operator is not defined.
So are we left to talk about time evolution purely in terms of like path integration or something?
So yeah, I mean, I guess yeah. Here it's hard. Yeah. So here the thing is, okay, you could say like maybe you could say that the dynamics is completely non-local, because to construct that operator, I basically have to know about the entire time evolution of both the left and the right boundary in general.
Right.
Yeah. So yeah. Yeah. So it's just not like a usual quantum field theory at all. Yeah.
Fair.
Yeah.
Do you have the characterization of the operator that's missing going from R to R hat in addition to Hamiltonian? Is there a characterization of?
Oh, yeah, I mean, yeah, so good. So this and sorry, I should say this is a statement about the von Neumann algebras. That's an important thing. Good. So yeah, so I mean, a nice boundary characterization, I would say no. Well, okay, in this case, no. There's one case in which we kind of have an idea. But basically, yeah, well, okay, we have we can write down a mathematical understanding of it, but we don't have like nice explicit formulas or something. So, okay, so the way that this works is that in the bulk dual, the bulk will be, this algebra will be dual to that. And for the bigger, it's dual to this. Okay, so what are the missing operators? Well, they're these operators here in the effective field theory. Then you can generalize this to a general setting.
Yeah.
And you basically, what you can do is you can say, yeah, good. There's I think, no, I didn't, I took this slide out. Okay, yeah, there's basically, there's there are two ways to take the large n limit for these local algebras. So the one thing I can do first is I can first talk about this algebra, which is where I've restricted within the finite n theory, I've restricted to the subregion of R. And so that's some algebra of operators, and for each value of n, it's equal to this. So whatever is the large n limit of that, they're actually going to be equal, because for each value of n, each finite value of n, they were equal. Good. And so what I can do is when I take that large n limit, I'll get some algebras, like say y bar, or something like that. And so this is the procedure that's like restrict to the subregion first, and then take the large n limit. But there's another procedure that I can do, which is I first take the large n limit, and I get a generalized free field theory on the boundary. That's still, a theory where I have these sort of local operators like this. So then I can restrict to Siberian functions supported in those subregions. And it turns out that in general, that gives me a different algebra than the one that I get from first restricting and then taking large n. Yeah. And so then basically, if you believe the JLMS modular equivalence criteria, then basically those extra operators that we're missing are operators that are obtained by finite modular flows within the finite n. Yeah. Okay, great. Okay, I'm running out of time. Okay, good. So let me just say, that this we can check that this works. So if I consider something like this, where I have a spatial slice like that, and I take the algebra in the diamond like this. Okay, lo and behold, we get the region you would have expected from the Ryuta-Kinagi formula. Okay, but I told you that the subregion subalgebra duality is supposed to generalize that, so that it had better apply to some cases. Good. So if I have bulk subregions that are not bounded by a boundary anchored extremal surface, then those are the bulk subregions that are outside of the Ryuta-Kinagi prescription, the subregion duality framework. So for example, something like this yellow region, which is bounded by a non-extremal surface, or something like this pink region, which has no operators near the boundary, those are not described by subregion duality, but they are described in terms of the subregion subalgebra duality. And the key to this is actually the loss of the Hamiltonian. So what it means is that in the large n limit, so here's a cylinder of the boundary with time running upwards. This time band here, so a time band is just the region between two non-intersecting Cauchy slices of the boundary. There's actually a non-trivial algebra of operators associated to that time band. And because there's that non-trivial algebra, this is the kind of algebra that allows us to describe these weird subregions of the bulk. One can actually deduce the bulk dual using a generalization of this time-like tube theorem argument to figure out what the bulk is. But okay, I won't say more about that. So for example, in the BTZ case, so here's the boundary cylinder. Imagine identifying these left and right lines. Then on a bulk time slice, I'll probe this annulus region. So this is not bounded by some extremal surface, but we can probe that region. Good. If I want to draw it on the Penrose diagram, it's this nice spherically symmetric region that I get by shooting light rays into the bulk like this. Okay. So what about those deep bulk subregions that don't probe the asymptotics at all? Good. So we have these non-trivial time band algebras, and they in the bulk, they're dual to operators that reach all the way out to the boundary on a Cauchy slice. So they have all of the near boundary operators. And so in particular, in the bulk effective field theory, the algebra of operators in the interior region is actually what's called the commutant, is what's called the commutant of that algebra. This is just the set of all bounded operators that commute with every single operator in this time-bound algebra. Now, let me emphasize that the finite n analog of this algebra, of this algebra MT, that's again, that's where we have the full algebra of boundary operators. We get a type 1 algebra, and that has a trivial commutant algebra. So these regions that are purely in the bulk, you know, the operators in those regions are these commutant, they're described by these commutant algebras. And so those bulk subregions are purely emergent in the large n limit. They come out of this large n limit where we get a non-trivial commutant structure. So for example, let me draw the picture in vacuum ADS. So if we had that uniform time band in vacuum ADS, we probe this annulus region, and the commutant probes this region in here. And in particular, if we go to the space-time picture, it looks like this. So we have a time-band algebra that probes sort of the region between the boundary and this blue surface, but the commutant algebra is exactly probing this finite causal diamond in the bulk. Okay, so because I'm out of time, I'll skip this last section on superadditivity. But if you have questions, let me know. The general idea is basically that there are additional properties that are violated in the large n limit about how we construct algebras of operators by putting them together in certain ways. And that can be used to understand things like these holographic quantum tasks. Okay. So good. Good. Okay, so coming back to so just to conclude, coming back to these questions that we wanted to answer, what we found is that these physics in local space-time subregions of the bulk can be described by emergent type 3-1 algebras on the boundary. The causal structure was related to properties of those type 3-1 algebras. And I discussed it briefly, but not in much detail. These infalling times can be constructed using what are called half-sided modular inclusions. And all of this comes out of this non-trivial algebraic structure that we obtain when we think about perturbation theory around the large n limit of the CFT. So for future directions, let me just say that I think there's still lots to be done with this. We can understand new algebraic probes of the bulk geometry. So you can think about the emergence of these type 3 algebras as particular probes of the bulk geometry. They're refinements of sort of previous entanglement-based probes. I think there's lots to be learned from understanding that. We can try to study the emergence of the black hole interior, and using these infalling times, can we find some signature of the singularity? Because we know that that at some point, if we have these infalling observers in finite proper time, they're going to see the singularity. And then finally, what happens when we start putting non-perturbative corrections into the story and they're forming these bulk EFT algebras? The ADS CFT picture would suggest that we should obtain these type 1 algebras for the global picture, but how exactly that works is still something we don't understand. So thanks for your attention, and let me know if you have questions.
For me, first question is what about perturbative corrections? Because what you're saying is really strictly n to infinity or G Newton equal to 0 limit. If you look at perturbative corrections, for instance, even in the definition of what is a gauge invariant operator of the bulk, then things become much murkier, right? I mean, that zeroth order is very easy to define invariant and physical operators are just transverse gravitons and all the matter degrees of freedom. They're all physical, and you can construct local operators in the usual manner. As soon as you go to the next order in G, you start to see that you cannot define properly local operators. You need non-trivial dressings that cannot be local because otherwise Gauss's law will be violated, etc. So how do you deal with actually the next few orders in G Newton before going to
Good, yeah. So for the next So from the bulk perspective, you have to do exactly what you described, which is sort of construct these perturbative dressings, by sort of attaching Wilson, gravitational Wilson lines to the boundary, and constructing operators like that. I guess, recently there have been sort of other approaches by studying deformations of these algebras, where you start taking into account things like just the Hamiltonian constraint. So I guess, okay, yeah, I think what we would say is that from the boundary picture, we believe that if you go to any finite order in perturbation theory, then this sort of type 3-1 structure will actually survive. Good. But if you can do these, yeah, you can do these other approaches where you suppress, yeah, good. Basically what you do is you allow certain fluctuations of the geometry to remain large in the G Newton goes to zero limit, not large as in they're growing with G Newton, but order 1 and the G Newton to zero limit. And then that gives you some sort of notion of a non-local dressing. So it's not like an explicit dressing within the bulk field theory. But basically, morally it's equivalent. It's morally equivalent to taking these sort of gravitational Wilson lines and adding these charges at infinity that describe that. So yeah, I guess and that does actually deform the type of algebra. And basically, yeah, that's because we had a center in the algebra when we included, yeah, when we start including those charges. And talking about 1/n perturbation theory, then we have charges like the Hamiltonian and more general charges that we have to dress to infinity. But that's like imposing sort of the invariance under large gauge transformations. Whereas for invariance under sort of local diffeomorphisms, at the moment we don't know how to do that in the boundary theory. Yeah. Yeah.
So in HKLL, right, you need to actually know what state you're working in to do the explicit construction. And so do you have a way of, when you take your large N limit with a particular state, like knowing beyond any other, like, can you do it beyond cases we already know? Or do you know which?
Yeah, so
like from the CFT perspective, then like which background I'm supposed to be solving a wave equation in? Or
no, yeah. Yeah, good. So yeah, so I guess in general we believe that for any classical solution of like the supergravity equations in the bulk, there should be a sequence of CFT states that are describing those, but explicitly describing those in general is very difficult. So that the cases in which we know exactly what bulk geometry you're going to land on are the case of like the vacuum state and the thermal state, where we know exactly what the right sequence of state in the boundary theory to study is. Yeah.
But we don't know any of the other one, any beyond that.
I think not in complete explicit. Yeah, we don't have a complete explicit description of things beyond that. Yeah. We believe that such sequences exist. Yeah. Yeah.
Maybe a slightly vague question. So do you have like necessary or sufficient conditions in terms of algebras of CFT that guarantees the emergence of some gravity description in the limit? Like suppose I have a sequence of the inclusions of type 3 algebras in the CFT. Are there conditions on this sequence of type 3 algebras that you can put forward that would ensure there's actually a gravity tool?
So I guess good. Okay. I mean, I guess okay. Yeah, I think. Yeah. Okay. Good. So I guess okay. Yeah. So we can ensure that there's a local dual theory, basically by yeah. Okay. Yeah. So yeah. Okay. So let me say. So like for example, like the yeah. Okay. The description of the thermal field double in the eternal ADS black hole is supposed to be general. And so in particular, there's a condition on the large N limit of the thermal correlation functions that's necessary in order for that to be type 3. And so if there's a then if there's a local theory that's if there's a local theory that there's a local effective field theory on a geometry with a background, with a causal structure that's non-trivial, then the algebra had better be type 3. So there is there's a consistency condition on the thermal 2-point functions in that case.
The condition on the spectrum is in a sense the opposite of what Maldacena used to reformulate the information paradox. Because in his construction, right, it noticed that if you have a CFT with n finite, you have a discrete spectrum, and in a discrete spectrum, a correlator never goes to 0 exponentially to all times.
Right. It always goes to
While here you want a discrete continuous spectrum, right?
Here you want a continuous spectrum. It's true.
Let's thank Sam again.